Welcome to the ESDIS AIML strategy session. I was talking to a colleague as we were walking in, and he said, "This looks like the most popular session there is." I said, "It's because I put AI in the title." We're actually going to talk about metrics. Okay, we are going to talk about AI and ML. Yes, we are. So I'm going to give a quick overview, then we're going to get into the meat of this. Trevor Lang, Clement Lee, and as a surprise, we've got Corey Krause over there talking about what we're doing with the Earth Data MCP operations. Then Jason Gilman from Element 84 is going to talk to us about agentic queryable Earth. Part of that is how he's going to be leveraging some of the tooling that ESDIS has put into place to achieve his goals. And then Tim Goff and Jimmy Sanchez are going to talk about the very, I don't know what surfing the digital wave means, but it's...
Stay tuned.
Yeah. It's about analytics in AI and our operational systems in ESDIS. Similar story for OB and Hanwai for the municipality of the Earth Data Cloud. So, NASA ESDIS, which is the organization above ESDIS, Earth Science Data Systems, put together, with our help, an AI strategy document for FY27 to FY30, which basically boils down to the following, once I get this out of the way. So the four strategic pillars are infrastructure, how we're going to provide the foundations for leveraging AI in our domain, then work in production, how we produce our data at scale and how AI is going to assist in the efficiency of that, how we're going to improve access to data using various AI agents, etc., and then how we're going to analyze the data to produce the science. What we're going to talk about today is going to hit three of those pillars: infrastructure, production, and access. This has suddenly stopped. There we go. So with those four pillars, how are we going to measure our success in achieving those goals? Our success measures are reducing the manual burden of the production of our data, increasing the success rate of our searches. One problem we have found for decades is the ability to find the right data or discover the right data. So we have capabilities deployed and in progress for improving that state of affairs, reducing that mean time to science, which is a huge percentage of researchers' time and effort, and the number of AI prototypes we get into an operational status, of which we have one today, do we not, Trevor? The Earth Data MCP is in production. Well done there. And then finally, how well our new mission data products are positioned for AI usage. So what is ESDIS doing about all this? We're producing natural language parsers in the Earth Data Search application. We're writing, we have in production MCPs, the Earth Data Model Context Protocol Service, CMR NLP endpoint, which is soon to be leveraged by Earth Data Search. And in our infrastructure area, we have ways to improve our cloud cost efficiency by leveraging AI and looking for anomaly detection in our operations, odd usages of our data, odd occurrences within our logging being analyzed by a machine rather than a user, which should speed it up and make it more cheaper. And then we're going to look at how those tools and foundations are being leveraged by the outside world. Currently, we have the Odyssey's accelerated knowledge discovery using our Earth Data MCP, and Jason is going to demonstrate how his agentic queryable Earth is also going to be leveraging the Earth Data MCP. And that is the introduction. So let's get into it with Trevor.
Hi, everyone. My name is Trevor Lang. I work at LM84 supporting the EED3 contract. I'm going to be giving a talk on the Earth Data MCP server today. After me, we'll have Clement and Corey talking a little bit about some more work that we have going on within EED. Let's see if I can. Here. So just click. There we go. Like I said, today I'll be talking about the Earth Data MCP server. Before I kick off, I have a few questions for the crowd. How many of you all are using AI often, like weekly? Okay, awesome. How many of you all have worked with MCP servers within your AIs? Cool, good bit of people. That's good news. So the Earth Data MCP server, before I jump into that, what are we going to be talking about today? Today we'll be talking about what is the Earth Data MCP. We'll be talking about why Earth Data needs it. We'll get to see it in action quickly. I'll talk a little bit through how to connect to it, the full tool suite that it offers. If I have time, I'll dig into a little bit into exactly what we built and what we see coming next. All right, so what is the Earth Data MCP server? Before to understand what the MCP server is, this is for all the people who didn't raise their hands during the MCP question, the Model Context Protocol is an open standard published by Anthropic in 2024. The goal was to create a language that AIs would understand so that they could securely call tools on their own and access data directly from systems. It's a standardized integration. It works the same across all of the AI clients that support it. That'd be Claude, Cursor, VS Code. You can build custom applications with something like LibreChat. We'll see a little bit about that today with Jason's talk. You can think about it like a plugin system or an app store for AI agents, but it's portable and vendor neutral. So you can take the same MCP server from Claude and run it in ChatGPT or what have you. Just to visualize it a little bit, you have a user. That user uses an AI client. This is their ChatGPT or Claude. That AI client can install an MCP server. When it does that, the client learns about what functionality the MCP server has, and the AI itself can call APIs to receive data and return them back to the AI client. The AI client can then contextually format that response based on the user's query to try and give them the answer they're looking for. The AI negotiates the tool capabilities. The server decides what tools to send, what data to return to those tools when they're called. And all the user has to do is ask a question in plain language. So why did Earth Data need this? AI assistants are becoming a very common starting point for research workflows. CMR, obviously very rich. It's got authoritative data, but it does require a fairly precise API syntax, bespoke vocabulary, and some institutional knowledge to be really effective querying it. Without something like the Earth Data MCP, an AI might receive a question and rely solely on its training data or hallucinate an answer. This could lead to incorrect data set names, abstracts, DOIs, access URLs, those sorts of things. Without an MCP server in place, researchers and other users are likely encountering this unguided, unreliable AI over the reliable CMR metadata. The MCP makes the CMR queryable by AI in natural language with verified results directly from the CMR. It allows Earth Data to become a foundation powering these AI systems, not something that it has to work around to get its answers. So with that said, I'll show a quick demo here. Some of you may be familiar with this screen. This is Claude Desktop. This is kind of my tool of choice. So today I'm going to show you how to connect to this MCP server using a tool like Claude Code, and then show you a very simple example of what the MCP server can do. So in order to add an MCP server in Claude, this is very similar in all the applications, but they all have different terminology. I can go into settings. Claude calls these connectors. On this connector screen, I can add a custom connector. You can see here, Claude has some integrations that they ship by default, but you can add your own. So I'm going to quickly copy and paste from a different window. You can name the server anything you want. I'll call ours Earth Data MCP. And you define a URL. This is it. The name doesn't really matter. That's just how it will be referred to within your chats. The core of this is the URL. Any AI client that supports MCP servers will use this same URL to access the MCP server. So when I add this, provided the internet's working well, we can see the AI client, Claude, made a connection to the Earth Data MCP, and it exposed 7 tools here. I'll dig into those tools a little bit more later. Don't worry about those quite yet. But these are the tools that the MCP is providing to the AI client. So now that that's added, I can take a query. I've got one pre-baked here. So here, I've got a pretty vague query. I'm doing it intentionally vague to kind of show the capability here. I'm asking, I want to explore what data NASA has available for the extreme winter weather experience in Texas in the early 2020s. So with a vague query like this, Claude, my Claude agent, can determine what I'm trying to figure out and the best way to answer it. Right here, you can see it's searching the web first. This is just trying to familiarize itself with the particular event I'm trying to talk about. You can see it's identified the Great Texas Freeze. It's identified a temporal range of the 11th to the 20th of February 2021. And it's identifying which physical variables might be most interesting to explore this type of event. Once it's determined what it's searching for, it can use this Get Keywords tool to search for the correct vocabulary to use from the GCMD keywords. You can see it's identified surface temperature as an interesting variable, and it's fired off a Get Collections tool request. Inside these Get Collection tool requests, you can see the different parameters we're passing along. A keyword has granules, a temporal range, and a spatial range, as well as the fields property, which we provide to allow the AI to reduce the amount of context it needs to consume to answer a particular question. See, it did 2 collections requests, and now it is providing me with a summary based on the data it received from those collections requests. So this is not data that is stored and trained on. This is data that it has grabbed from the internet live from CMR to then pull into its context and influence the conversation. So here we can see it performed 4 granules calls. This is important because just because a collections coverage matches, that doesn't necessarily mean you'll have data during the particular area of interest. So it's fired off 4 Get Granules requests to confirm that there is actually data for this event. And I won't read through all of this, but it's summarized a lot of the details. This is one of the great things about this is it will, based on how the question is answered, what it knows about the user and what knowledge level they have, it can contextually generate this response to the user. You can see it's identified 4 collections that would be interesting to explore these variables. And finally, it has provided me a jumping off point to open this up in Earth Data Search, or suggested using the Earth Access library to explore this programmatically. So now from here, The AI agent could do any of those things. It could go to Earth Data Search to look for the data, or it could help the user generate Earth access scripts to access this data in place. So I'm not a geoscientist person at all. I've been able to do some really cool stuff with this tool just by working, integrating with other MCP servers, composing tools together to automatically create Python notebooks, runnable experiments without ever touching code myself. So I'll stop my demo there. Let's see if you can revert me. Thank you so much. Okay, so connecting to the server, like you saw me do, all you have to do is take this URL, find the right place to put it within the AI client that supports MCP, put the URL. If they ask you for a protocol, we use streamable HTTP or HTTP, sometimes it's referred to as, and there's no authentication required on the server currently. This would work with VS Code and Copilot, Cursor, Claude, custom systems like LibreChat. All you do is add this endpoint, and then your AI immediately gains the ability to search NASA data. We've talked about a few of these tools here. There are 7 tools total currently in the MCP server. We've looked at Get Keywords, Get Collections, and Get Granules. In addition, we provide tools to access the services that are available for different data sets, the different tools that might be available. We have a Get Citations tool, which allows a user to search for data sets and find which papers they've been cited in, and also take papers and find out which data sets were also cited. And it can explore the scientific variables associated with particular data sets. When an MCP or when a client connects to the MCP server, we deliver a server prompt that tells the AI agents the best way to use these tools. You can use them individually if you don't want to use it that way, but we inform the agents of this discover, verify, access workflow, where we encourage the agent to first find collections that are relevant using Get Keywords if it needs to find particular vocabulary, and the Get Collections tool to actually find the dataset metadata. Once it has particular data sets, if a user has asked for a specific area of interest, the AI agent will verify using the Get Granules tool that data actually exists within that particular area of interest. And finally, once it has data that's actionable, it will encourage the user to work with that data, whether that be opening it up in a web UI like Earth Data Search, or taking advantage of the services it has available, or offering suggestions to use the Earth Access Python library to access the data programmatically. The 3-step pattern is here to prevent the most common failure point. We've all seen it. AIs hallucinate and they sound very confident when they do it. Sometimes it's hard to catch. So we are aiming to convince these agents to search this way so that they provide more reliable responses. A little bit on the architecture and philosophy here. When we first started building this tool, we started building out an embedding search-based system that would store all of the CMR metadata, augment it, allow it to be searched via embeddings. What we realized around the same time as we were starting to build this is that the foundational models, their context windows, their training had all improved so much that just by providing the data at the right time, they can answer these questions just as well. So rather than building out a dedicated pipeline, we just built thin wrappers around existing CMR functionality and allow these AI agents to access CMR. What we've ended up with, 7 tools, all built around CMR functionality, direct real-time queries to the NASA CMR, comprehensive server and tool prompts that inform the agents how to use it. And we just came to the realization that we may not need these complex wrappers around these systems if the AI can get the data directly. So in terms of what's next, We really want to measure what matters, so we're working to set up observability tooling to help us establish accuracy so we can improve the results over time, allow us to iterate the prompting. We are listening to the community. We really want to establish some feedback mechanisms on this and drive hands-on engagement with different DAC teams or broader user community. Surface real-world gaps through testing this with real users. We want to grow the audience, so we hope to develop workflow guides for specific use cases. We want to meet these users and the tools they're already using day to day. And we want to share our updates in community forums. And next, we want to continue evolving the tool set. So right now, we don't have any spatial support. The LLMs do a pretty good job helping the user out with this part of the search, but we would like to provide some direct way for users to get good geometries for their questions via natural language. We want to look at doing on-the-fly data processing with tools like Harmony. We'd like to experiment with additional tools like to enable dynamic visualizations right in a chat using map visualizations, build in some operation-specific guidance, and closely integrate with Earth, or more closely integrate with Earth access to allow seamless data download. So we'd really love to hear from you all. If you've tried it, come find me. I'd love to hear how it's working, how it's not. We want to know what data you guys are trying to find, what AI clients you're using, and what might be confusing or missing from this MCP server. Well, thank you all for your time. Appreciate it. Next, we'll have Clement Lee. And stay tuned for Jason's talk to see how this MCP server can be used.
Thanks. All right. All right. Thank you, Trevor, for introducing us to the MCP server that we have. A lot of cool stuff, and hope you guys start using it. Tell us how to improve it. My name is Clement Lee. I'm with Raytheon, also working on the ED program, particularly with CMR. There, we are building some of, kind of diving a little bit more into like AI ops, what we call AI ops. So for those that don't know, CMR is a pretty core gateway as like part of many pipelines that help a lot of our users get to the our science status that they need, be able to search it. So being CMR, we need to make sure that the APIs, CMR remains reliable and also performant. So in order to do that, instead of having some dev that's just like sitting in front of a computer 24/7, it's a lot more helpful to introduce some AI operations into it to help lower some of the many problems that a lot of industry is facing when it comes to ops, such as decreasing the time to discover a problem, decreasing the time to recover from a problem. And part of that is to have that automation, but also to be able to do some analysis, and possibly when you get confident enough in it, maybe even kick off some recovery process that it finds that worked in the past. In terms of recovery, tribal knowledge is a real big thing, right? When you're working with ops, you know that you've seen a problem, you know how to fix it, right? And a lot of times this usually comes and goes with the developer or any kind of engineer that's working on the problem. In order to reduce some of that tribal knowledge, that we want to reduce some of that tribal knowledge. And also, one more thing, why we want to use AI ops in this way is that a lot of logs are pretty sparse. It's a little bit different than metrics that are well data engineered and well thought out, and there's a clean pipeline for it. A lot of logs that for example, CMR has is like kind of pretty sparse. A lot of different fields, a lot of like different names for the fields depending on how the search is being done. So this is why we are introducing AI to the solution. So where AI ops is really just using machine learning or traditionally using machine learning or AI to help look at a problem, help digest like a huge amount of data into something that's actionable. And this, the thing that we built really just takes a prompt, either a schedule report or some issue that's detected or or a chat interface that we have built, put it through this agentic workflow, and it interfaces with our database and outputs a report. There are, as I mentioned, a few applications, the report generation, the chat interface, but all of this is just this agent that you could kind of plug and play into different applications and then use it to generate the same output. The technical core of it is really LangGraph. LangGraph is a pretty powerful API library that you could use to help orchestrate workflows. It's a little bit more rigid than something like, say like an agent, a client that's connected to our MCP, which is able to like select the tools. We want this a little bit more rigid because we want a lot of the make sure that the data is not hallucinated, the results are not hallucinated. So this allows us to put a lot of safeguards in place, a lot of our like validation, a lot of like failure loops in place in order to make sure that the agent, the results that the agent is producing is good and usable, and it's not misleading us, especially in something so crucial like CMR. Let's see. So just going down this one on the left. No, you're right. My left. The user provides a prompt, and what happens is that we inject the context about a database that's happening. For example, like the schemas, some sample logs in the data, so the agent will be able to know what's inside the database and be able to query a little bit more efficiently. Then it generates a series of hypotheses on how to generate like queries and hypotheses to like answer the question and find data about the question. These queries are validated, and if it's not correct, then there's a iteration loop to correct the queries, so you don't just have a bunch of like waste a bunch of tokens on bad queries and failed queries. Once the query is all validated, we could, there is a human in the loop process in this too, but when that's all good, it goes through, the human in the loop could be skipped as well. It's like a flag, but once the queries are good, we put it to the query executor, execute a query, it generates a bunch of results back. If the results evaluator looks at the data, and finds that, oh, this answers a problem that the user is asking about, then okay, we're going to generate a report, generate some graphs, generate some tables for you to look at and verify. If not, then it's going to go through again and generate some hypotheses, dive deeper into some previous queries to get the answer that that they want. And with that, I am going through a demo. So what we built was we put the agent that we built that we talked about earlier in front of a chat interface. So this allows the user to be able to ask a question and have the results come back in the same place, and then you could continue to iterate on the findings that it had. Is it going? It's going. Cool. So here, this example here is that we're looking into something that we saw last June in 2025, just to take a look at some of the user patterns that's happening, then see if there's any high usage or like query patterns that might have explained some of the degradation that we were seeing. And So what you see on this left side, let me just go back a little bit. What you see on the left side is that it injected some of the context, right? Such as like it queries some sample rows. It gave the schema of the database, connected to the database. So all this is done upfront. So you give the agent the context that it needs to be able to generate a bunch of queries. It has since generated some queries. It's able to like see the types of hypothesis. In this case, it's trying to look for unusual query parameters, and it generates 5 queries. And what's nice about this is that when it returns the queries and returns the results, it returns it in like a table form. So as an analyst, I can kind of fact check what the LLM is saying. It is claiming. That way you could make sure that it's not hallucinating, and also take a look at data yourself. As it goes forward, you see on the left-hand side, it started the second iteration. It went through the first one. The data wasn't sufficient, so it went through the second iteration of generate a bunch of other queries to look through. You can see that the queries are pretty sophisticated. They do statistics on it, like 95th percentile in some cases. It's time series. And I think we're getting towards the end of, let me see, a little bit far behind. You could sort through it to explore the data a little bit. And once you get towards the end, then it will generate like a nice little, let's skip forward a little bit, generate like a nice little summary of the findings that it had, and also some recommendations that it might suggest. But more importantly, as it's going through this entire process, it is collecting anomalies and patterns that it's finding. So once it gets towards the end, it's able to generate some plots to help the user, to give an answer to the question that the user is trying to look for. And more importantly, once you get to the very end, you could continue to ask about some findings that it had, so you could iterate on it to really dive deeper with the human in the loop. And this is really intended to be more of like an aid to the analyst, to help get the data in front of them a little bit easier, help them explore it, as I said before. With tribal knowledge, a lot of times, as a new engineer, you come in, you look at all these logs, don't know what's going on. This kind of gives you like some ways to like have some queries to be able to like go into, see what type of data there is, and really just be an aid to the engineer. I think I will go back to the slides now. I guess while we wait, I could talk a little bit about what we're going to do next. Some like lessons learned about this is that LLMs are really powerful, but for something so critical, the engineering that goes around this these days is building harnesses around the LLMs to make sure that it gets through the failsafe, get through some.
Is that yours?
Yes, that's mine. Yes, to really like put like safeguards around the LLM for it to like make sure it doesn't get to the data, doesn't wipe out your database, for example, and also. A lot of it really is data engineering, which is something familiar to us, right? You provide all this data to an LLM for it to like query and make and generate like assumptions out of and generate data out of. But if the data that's providing is not clean, not easy to query, it ends up being the source of the problem. So like it becomes something familiar where it's like data engineering and building harnesses around these LLMs that that got so powerful. That said, some of the next steps is that right now this is really implemented with the search logs that we have at CMR. We kind of built like a search expert, you could say, but we could start adding some other data logs, some other log data to allow some deeper analysis to be able to like really root cause some of the problems like a CMR analyst. And with that, I think I'm done. With that, I will hand it to Corey to talk about some next steps.
Hey everybody. So we showed off some of the cool stuff that we can do, but I'm gonna tell you a little bit about the general update and the plans for the future. So we talked a lot about the Earth Data MCP server. This is where we are right now. And we have search and discovery and access and effectively ops and infrastructure. Those are the two sides that we've been dealing with two different teams. So with the Earth Data MCP server, we're assisting users and AI clients with data discovery. We've shown this off. But we also have the CMR chat, which is effectively a LLM, natural language processing inside CMR that you can talk to conversationally and get information about CMR. You can go directly to the site and just talk and see and understand what's in CMR to get information about that. It's something that we haven't really shown off. Okay, it's not there. Also doing the CMR log analysis, supporting and continued understanding and improvement of the CMR. We want to understand how it's being used, debugging, making sure that the clusters are working correctly, make sure everything's balanced correctly, things along those lines. Very briefly, also Trevor talked about CMR spatial search performance improvements. We want to make sure that the polygons that you get back for the areas that you care about are actually accurate and that we're not getting hallucinations. Making sure that the performance is good. Some of the issues that we've been dealing with is that people don't like it when it's slow. AI is a little bit slower. And even if you're getting everything accurately and you're dealing with AI, some people might want to just go back to the old search and say, this is actually a little bit quicker if I just do it this way and I put in the information I want exactly and I know exactly what I want. So we have to make sure that the AI systems are actually fast enough so that when it's thinking, you know that AI is doing something and it gives you the information back the way that you want it. So this is where we are. But in order to get to what's next, we would love a bunch of feedback. The way that our contract works is we kind of get feedback from the users. We understand what they want. We write tickets. We talk about those tickets. We spend a lot of time doing this process. And it would be fantastic ammunition if we went in and said, the Earth Data MCP server needs this new tool. I saw a bunch of people actually, when Trevor put up what 7 tools are available, take a picture, and it seems like, oh, this is what I can do. But I don't want people to think that those are the 7 things that you can do. More so, in a year, you could do 20 things, but you need to tell us what those other 13 things are so that you get access to the things that you care about and that we can build it into the systems and build it out for you guys. And that's something that we would absolutely love to have a process with the entire community in order to build out those tickets, get it in our pipeline, get the engineers working on it, and give updates throughout the year on improvements to MCP. We haven't talked about NLP, natural language features in Earth Data Search at all. That's going to be landing really soon. So when you go into Earth Data Search, right now you have just the standard querying, you look it up, you search the granules, the collections that are available to you, but we're building out a conversational approach just like any other LLM where you talk to it and it gives you the data that you care about. So that's going to be coming very soon. It's not in production right now, but it's in lower environments. CMR chat quality and capability evolution. Anybody who's working with the CMR chat, please do the same thing. Tell us what you actually care about. Tell us how you would like to be using it. And then more just the standard log analysis and vulnerability detection. We're implementing AI in order to debug faster, understanding what the issues are, make the fixes, and go from there. But we really want to have a process where we talk to the community, understand what everybody wants with natural language processing, with the CMR, with MCP, and with the automated CMR improvements. So if you're seeing any issues with the CMR and find and can figure out kind of what the issue might be if some of the data isn't indexed correctly, if we have to do resharding, anything along those lines. We're dealing with it on our end, but a community discussion is really warranted. I want to thank everybody for coming to this session so far. Trevor and Clement showed off what we have in AI right now, and would really be interested to hear your feedback and go from there. So I thank everybody for your time. And if you have anything, please don't hesitate to contact me, Trevor, or Clement with fixes in the future. And I'll be very quick and hand it over to the next person, because I think we took a lot of time already. Okay.
Hello, everyone. I am Jason Gilman. I'm the Director of AI Applications for Element 84. We're a professional services firm, and we specialize in geospatial software, cloud computing, AI, and a lot of other things. I'm going to be talking to you today about a new tool that we've built called Agentic Queryable Earth. And what it is a general purpose agentic tool that can handle geospatial questions and provides conversational traceable analysis across Earth science data. I've got a lot of slides to get through, so I'm going to go quickly. I really would have liked like an hour, I think. So some of the things that we've worked on before this that fed into it, and we learned lessons. One of those was a, oh yeah, that would be nice if that wasn't in the way.
Keep going.
Okay, one of those was a climate data chat for NOAA, and this started about 1.5 to 2 years ago. And this was a prototype, and that's kind of wrapping up pretty soon. But it lets you ask, geospatial questions. It searches a knowledge graph. It can analyze data. Another one that we've worked on. Get the slides. Okay. Another one that we worked on is Chat GSFC. And so this is an agentic tool for NASA internal users. And there's about 9,000 to 10,000 people who are using it now. And it's not particularly like a geospatial tool, but it can handle general knowledge tasks. And we've had a lot of like domain specific challenges with this one. And we learned a lot about handling big data with AI and how do you do that appropriately. We have a blog post on this you can read about. So I'm going to go through some of the lessons that we've learned, because these apply to what we've done with Agentic Queryable Earth. So one of those is don't reinvent the wheel, use open source agentic tools. And it's a pretty obvious lesson. But about 2 years ago, we were designing the NOAA system. There were existing open source libraries, but they weren't that great or didn't do exactly what we needed. But over time, they've gotten a lot better. And so now it's at the point where you can take these open source tools. They're also updated really quickly, so they are keeping up with the advances in AI. An example of this is like Chat GSFC is built on LibreChat. And so as new features come out, new things adapt, like sub-agents, running code, skills, all that sort of stuff, that just arrives for us for free, and then we're able to like roll that out. The other thing is like agents are only as good as the connections to the data and the tools that they can use. One of the things when we first rolled out Chat GSFC is it was a system where users had to bring their own data. So that meant they uploaded spreadsheets and documents and things like that. But that was pretty limited. And we realized that in order to enable more that you could do with this is to be able to connect to the data systems that people work with, the things that have their data. And then additionally, you have to provide the right tools. If you're doing geospatial analysis, you need geospatial tools. Or if you're designing spacecraft, you need the right like 3D rendering and things like that. The one big thing that I think most people miss is memory with agents. Agents need a way to remember what they've done before, what's happened. You need traceability as it's doing things so that you can see into it, and provenance. You need to be able to see, where did this answer come from? What was provided there? Additionally, it's nice for agents to have like a scratch area, right? If they're going to go out and fetch data, where do they put that data? How do they work with it? Does it just all go into the context for the LLM? And that can run out. And that's probably the biggest challenge and lesson with this, is that the LLM context is very limited. And so LLMs have no memory. They only know what you send them. So if you ask a follow-up question, what gets sent? everything, like everything before that in the conversation, like the system instructions, what are all the tools, what are the APIs for the tools that it can access, what messages you sent, what its answers were, what it thought about that, what tools it called, and all of that fits in there. And this is the thing that impacts everything. So it impacts the cost that you spend answering questions. It impacts what is the tool design, how granular the tools are, how big the documentation is just for using those tools and things like that. And so we've taken all these lessons and put it together and try to follow like these best practices that we've learned into this general purpose tool called Agentic Queryable Earth. It's built on open source software. So LibreChat is the foundation, works pretty well. And we've extended it to add things like mapping. So we have layer rendering, and you can show rasters and vector data. And it's also given it the memory. The data storage extension here connects it to another service I'll talk about later, Agentic Data Storage. And we've also provided it code execution with built, like it's a sandboxed Python environment where it can write code and then run and execute it. And it comes prepackaged with a bunch of geospatial tools. And then it has a bunch of image analysis things like object segmentation, like what is where are the solar panels in this image? Or being able to ask an LLM, what am I seeing here? And also natural language geocoding so it can figure out what the area is. But now tools are only as good as the data that's available. So it's pluggable. You can add in your own data sources, but we've added in our test deployment of it. AWS Open Data has an MCP that just came out recently. We got early access to it, and it works really well. And this gives you access to now all of the open data that AWS has. And now it's great that NASA has the Earth Data MCP, which it means those tens of thousands of collections in the CMR and over 2 billion granules that are there. We can now like search all of those efficiently, find the right data, and it makes it really easy to plug into AI tools now that they're providing it via a standard open protocol, the Model Context Protocol. To enable us to like do more with the data, we've added a couple other MCPs. One of those is Earth Access. So if you're accessing NASA data, they want to have like some records of that. And so you have to use your Earth Data login credentials to authenticate that. We created an MCP that makes it easier for the AI to get those credentials. And also a firm's MCP for working on some specific fire detection use cases. That makes it easier to deal with firm's data. So I'm not going to try and do live demos. I'm not as brave as Trevor and the other people here. And it also means I don't have to switch. But I want to show later, you can come see me. I'm happy to show any one of you a demo. And also at the research showcase, I'll be showing demos. But here's an example of, I asked about like the LA fires from last January. And so what it did is it loaded a skill. We wrote a skill that helped it with that. And it starts searching the CMR. It executes geocoding. And by the end of it, we get a map here, which is toggleable layers. We can see like detections on a particular day. I can switch between seeing the fire bands or true color. And here I'm like showing a particular day, January 8th, which is one of the worst days. And we can see the firm's detections. And here is in true color. We can see the smoke resulting from that. This one might be a little small, but this is showing you in more detail. How does it answer a question like, show me the sea surface temperature from the Gulf yesterday? And this is right in as an example question in the Earth Data MCP tool. And so I asked it this, and it's able, it goes through it. First does in parallel, find the collections for sea surface temperature, and where is the Gulf? Find that. And then it finds the collection. It picks one, it searches for granules, and then it uses some SQL to pull out just the parts of the granule metadata it needs, and so on. Eventually, it writes some code, runs it, because it's a net CDF that it finds, and it needs a geotiff to display in the map, does that. And then by the end, you get a nice visualization here of the sea surface temperature. We know what the range is. We have the average. And you can follow on with this. I can ask it, hey, can you create a raster that shows me this date versus last year? And highlight the differences. Where were we hotter or cooler, et cetera. So we'll talk about some of the things that make our tool work well. And one of those is agentic data storage. I talked about that: memory, provenance, transparency, persistence. So a typical agent harness, and what an agent harness is it's the code that implements an agent. and that knows how to talk to LLMs and invoke tools. The typical way that they work is you ask a question, it talks to the LLM. What should I do? It says invoke a tool. We invoke it, we get back a big response, and the problems happen with what do you do with that? The typical way is we pass that to the LLM, and that's just the way that they tend to work. We give it the response back, and this implies a lot about how you're designing MCPs and how big that response is going to be. And you have to be careful because this starts to fill up the context, and the LLM has to now make multiple tool calls, and now it has to deal with a lot more. There's other ways to deal with this. So sub-agents is one way where you can say, okay, I'm going to give a whole agent its own context and go off and figure out the problem. Another way is code execution. We can tell the LLM, you have a code execution environment, and it can decide, I'm going to write code to call the tool, and it can get back the response and then slice out the particular parts of it that it wants. And this works. There's some questions here though. Where is that full tool result saved? Can I go look at it later? What if I want to get other information out of it? Do you have that traceability? So both of these work, the sub-agents and the code execution, but they're still, I think, missing something. An agentic queryable Earth can do both of those, but it has a different approach for just the default case of invoking tools. So this looks a lot like the first slide I showed you. We still ask the LLM what to do. We can still call a tool. We get back the full response. But the difference here is, what do we do with that response? We ingest it into agentic data storage. And what that is a new service that we put inside agentic queryable Earth, and it saves it into S3 in a bucket. We've got the metadata associated with that. What was the input? Where did this come from? What conversation was it part of? Which user? So we're making it secure. And then it generates an intelligent summary, and it's deterministic summary too. We're not using an LLM to do that. And it's a much shorter summary that we give to the LLM, so it doesn't take up as much space. And we also give the LLM a URI, and this is a persistent URI that sticks around and later can ask for more information about it. If we go into agentic queryable Earth, you can see there's a little disk icon that I'm pointing at. You can click that. This still might be a little small for you to see, but we can see here in reverse order, what were all the tool calls that were made in order to answer this sea surface temperature question. And each one of those I can expand and look at the data that was there. So I'll look at the natural language geocoding, and we can see what the input was. It was Gulf of Mexico. We can see the summary that we didn't have to give the LLM every single latitude and longitude with 10 decimal places of precision. We can just give it the bounding box and let it know, hey, it's here. You can do something with this more if you want, pass it to somebody else. It doesn't have to see that full data there in order to know what to do with it. And also you as a user have this visibility into what's happening. But what if it needs more, right? If we're going to do a granular access and we only give it a summary back, it might need to do more with it. And so it has SQL abilities, so it can search across agentic data storage and pull out specific details. It's very small at the bottom, but this is saying give me the concept ID. It's writing SQL, give me the concept ID, the time that it started, and the access URL. So it can pull out just those couple pieces of information. And so what we've done is we've inverted the data flow. Instead of pushing a giant response into the LLM, we've instead said, hey, I've got a big response here, LLM. What do you want me to do with it? Here's a little summary. And it can say I want you to pull out just these parts. And it can do that without having to write Python code to slice it out. So in summary, the Earth Data MCP is awesome. NASA's great for adding that in. It makes it really easy to just plug it into any tool. It was awesome. Trevor showed just using Claude by default it's not a geospatial tool. But you should continue doing that. Add Harmony was an interesting idea. I think Earth Data Access, we've built, and we could share what we've done with that. We're excited about agentic queryable Earth. It's currently being refined, but I'm happy to do demos for anyone. And if you're interested, please send me an email, reach out to me, come to the research showcase to see a demo.
Good morning, everybody. Well, it was when I practiced this in the hallway, it was morning. So I'm Jimmy Sanchez. I'm the platform product manager for the Earth Data team. I'm here with Tim Goff, who is our platform architect. And we're going to be talking to you about something called, we've been calling the digital wake. So as our cloud archives continue to grow, users are finding new ways to access our data. And the challenges that we're facing and that we're solving are no longer about just storage anymore. They're about everything that happens downstream when those access patterns begin to change. And so today we're going to go walk you through some of those challenges and the solutions that we're putting into place to address those. A little bit of background. So to put things into perspective, Earth Data manages over 128 petabytes of data, and we are distributing over 200 petabytes of data every year. And so with the adoption of AI, as that's becoming more popular, with machine learning and cloud computing and some of these missions like NISAR, we're seeing that those access patterns we're seeing access patterns that simply didn't exist a few years ago. And so we're having to put things into place to adjust to that. Instead of downloading just a few files or a couple granules like we were seeing years ago, we're now seeing that users are able to download entire collections and submit several billion small requests per day. And so with that, not only does the infrastructure have to scale, but more importantly, all the surrounding systems with that have to scale as well. Okay. So we like to compare this to a boat moving through the water, right? A small boat leaves a small wake, and a large boat moving quickly creates waves that affect everything around it. And so the same thing happens in our cloud systems. One user's workload doesn't just affect storage or bandwidth, it impacts authentication, metrics, monitoring. We're seeing it impacting our cost, reporting, and just even our overall operational stability. And so that's what we mean when we have the term digital wake. So this diagram right here, this shows, this is just one example. Every request flowing through the system here, it's creating telemetry that feeds eventually into dashboards, it's feeding into analytics, it's feeding into reporting, budgeting, and overall operational decision making. And so when our request volume suddenly spikes, those downstream systems that we're seeing, they experience the same spike as well. And so even if distribution keeps working perfectly, your metrics pipelines can quickly become like the bottleneck if they're not designed to handle that scale. And so how do we manage all of this, right? We don't rely on just a single solution. We have a multiple layer of protection solution we've put into place. And so the boating analogy really works well because when different conditions require different tools. So sometimes you slow people down, right? Sometimes you build stronger infrastructure. Sometimes you just absorb the impact. And sometimes you redesign the system so that the wake isn't even a problem anymore. So the first layer is prevention. We use automated and manual rate limiting. We have authentication controls in place. We do user outreach. And when necessary, sometimes we will actually block an abusive user or a user that is distributing like non-compliant behavior. And so what we found though is that most users, they aren't trying to cause problems, right? They're just often unaware of the downstream consequences of making millions and billions of requests in a short period of time. So the next layer is building stronger protection around the platform itself. Here we're talking about machine learning assisted budget monitoring. You're going to hear a little bit about that in Obi and Hans talk in a little bit. We're talking about anomaly detection and also some automated circuit breakers that we've put into place. So if something unexpected starts driving up our cost or our traffic beyond acceptable thresholds, we want systems that detect it early and are able to respond to it before it becomes a larger operational issue. So sometimes you can't prevent the wake, right? You've got to absorb it. Like Tim and I, we went kayaking last night. There's a boat that came by and, we had to turn into it. We had to absorb it and take some of the impact. We do that automatically by moving data between storage tiers. That's one way we do it based on access patterns. And so frequently accessed data that will stay, stays readily available. And then colder data will move into lower cost storage tiers. And so as demand changes over time, we want the storage strategy to change with it. Okay. All right, this graph here, this shows what that looks like in practice. Collections naturally move between periods of heavily active and periods of very little activity. So if we're able to use, we're using services like S3 intelligent tiering, that lets us to automatically respond to those changing patterns. We're able to reduce the storage cost without changing the user experience. And the user experience is a big part of it. We want this to be agnostic, what's happening in the background to them. And so, so far we've talked about managing the effects of the digital wake. We've talked about preventing some of the unnecessary loads, protecting the platform. So that's just one piece of the puzzle. I'm going to turn it over to Tim, and he's going to give you the other components. Thank you, Tim.
So Jimmy's talked a lot about the ways that we can avoid or protect against the impacts of the wake, but we can only prepare for what we can anticipate. Sometimes we're going to have to ride the wake out. We're going to have to hit it head on, like he was saying with the when we were on the kayak, a boat came by. Like similarly, the first time I ever went paddleboarding, I found out pretty quickly that like a big motorboat goes by real fast. You have to steer into it, so you hit it with the smaller side of the boat, the front of the boat, the bow, so that you're absorbing on the small part where it's more stable, and not on the side where you're much more likely to get knocked over. It's a bigger surface area, and you're less stable in that direction. So we have the same kind of idea here. As Jimmy was mentioning in the previous diagram, a key downstream effect of the digital wake is the impact on metrics as they flow through the system. And he showed the original approach. This is a more modern, updated approach that we're building out. So instead of taking the brunt of that on like the broadest side of our system and being knocked off balance, we're re-architecting our metrics and our ETL pipeline to use lambda-based workflows that scale is needed to absorb the impact on the front end on a smaller surface area, protecting downstream components that are less scalable, instead of passing the full load all the way through the system to be parsed at each layer. We're processing it once into a common data lake that we make available to every layer that needs it. We're not locked into one thing, to each system indexing itself or indexing it once and then querying it through a common framework. With metrics, once they're in a common data lake, we're able to use big data tools and AI tools to answer questions that would be really hard on such large and varied data without those tools. So we're using AWS services like Athena and QuickSuite to enable natural language processing and other insights that help us to understand and ask questions that we wouldn't build a system specifically to answer, because we would know we need to answer those questions. But now we can say, we can ask questions in natural language and get usable business intelligence. Finally, we've been talking so far about the digital wake as a destructive force that needs to be avoided or mitigated. But much like water skiing wouldn't be much fun without a wake, the digital wake is also an opportunity. So after all, we're in this situation, we're dealing with a digital wake as a symptom of our own success. It's not a problem, it's something we have to embrace and build on and adapt to it. And so embracing the wake means questioning assumptions and architectural decisions instead of thinking of every system that's egressing and providing data as a entirely separate system. We're looking at it as an enterprise so that we can streamline how we're responding and managing changing usage, and not have to put a lot of effort into each separate tool looking at this separately. We're working to enable users to log in using the identities that they already have, rather than necessarily having to register for Earth Data login. So we have, it's not fully visible in our production systems just because it hasn't been fully configured everywhere, but we're working to have Google authentication as well as ESA, European Space Agency, so that if they have their own identities, they can log into our systems with them. And we're rethinking how we handle backups by leveraging S3's built-in data protections and guardrails, so that we don't have to back up every single file in duplicate. We can back up the changes and back up the deleted files and make sure that what we already have in S3 is protected there. It's already got, however many nines of protection that S3 provides. And that lets us be a lot more efficient, but still be safe and protected. So in closing, AI and other evolving technologies, we're evolving. We're trying to figure out how to move forward and evolve and make sure that the systems are as usable and building as much value as they possibly can for everybody.
All right, guys. Guys, we'll be here all week. Thank you.
All you have to do was touch the button.
Yeah, just have it press it again. Mm-hmm. Perfected it. You have the PowerPoint?
Yes.
Yeah.
Yeah.
Mm-hmm. Yep. Yeah. Yes, I did. Yep. Hold on, let me just make sure.
Alrighty, excuse me. All right, good afternoon, everybody. My name is Obi, listed there, Oholiab, and I am part of the EED3 contract with Raytheon, and I am a product owner in the cost analytics team. And I'm joined here with my co-presenter as well.
Hi, I'm Han. I'm also on the ED program as a senior data analyst on the global metrics team.
Awesome. And today we're going to talk to you about what we're calling the municipality of Earth Data Cloud. Thank you. Alrighty. So let's just jump right into it. With respect to any municipality, there's 4 big components. We're going to talk to you a little bit about that today. The first is the residents, and those are who we call our tenants. So that is the DACs, the different organizations that have that live within that Earth Data Cloud. The second big piece is our city officials, which is our ESDIS, our civil servants, and the stewards of this data, and really those responsible and allowing us to do what we need to do with this data. The third is what we're calling that public utility and infrastructure, and that is kind of our organization within EED, which is that platform train. We'll dive into a little bit about that. And then we also have what we call emergency services. Something we really want to make sure you kind of leave with here is that none of this stuff happened overnight. It was a journey. I think it's a journey that we're all very familiar with. And just to put a little bit of some of the information we talked about earlier, when it comes to how big of a city we're running, as you heard Jimmy and Tim talk about 126 petabytes. I did a little quick Googling to figure out, using AI, of course, what that would look like on a piece of paper. So according to Gemini, that is 64 trillion sheets of paper. And that is, if we were to lay it side by side, it would go around the Earth on the equator 446,000 times, right? That's at scale. And for those curious, that is at 12-point font times New Roman on 8.5 by 11, right? So computer paper. So, I'll hand it to Han to really talk about kind of what allows us to run this city in such an efficient way.
So like Obi was saying, that we're building this municipality and it's built off of the metrics data lake, which is our reservoir of information. And a reservoir is basically a man-made lake that bridges water sources to address human needs like homes or buildings, agriculture. And in the same way, our data metrics reservoir bridges different data streams so that we can address the needs of our data users like DAC users, NASA, science users. And it is a centralized repository that has different streams of data, and you can use it as is with just regular reports, and you can also build on top of it using machine learning, getting advanced analytics, and making more visualizations. So historically, accessing data has been a really manual process. You're going to different sites, accessing, getting approvals, and oftentimes duplicating efforts just to get your data. Here, we're trying to move towards a more self-service model where you're accessing everything in one centralized, secure space. And you can also have user-derived data where you're uploading your own CSVs or Excel workbooks and building off of that. Overall, it's used to simplify access so that you can play around with the data and develop it further. The current data sets we have in our data lake is the cost data, S3 access log, CloudFront logs, EMS data like user data, product data distribution. And we're using a lot of AWS services like S3 to hold the data, and then Glue, which is like a water treatment facility where you're cleaning and cataloging raw data to feed into Athena, which is like a water pumping station, where you can run on-demand queries to pull out the exact data that you need. And from there, you can also move it over to QuickSight or Orbit, which is like a smart utility dashboard that you can visualize your data, validate your data, and create reports off of it. And I'll pass it back to Obi.
Thanks. So you saw one of the examples on there was that cost and usage data. So we're going to walk you through a little bit about the journey we've had with that and kind of how we've integrated with AI and machine learning to manage our cost. So first, left-hand side, this is going to be something that's you're going to continue to see. Three big questions when it comes to budget and cost is, one, we want to understand how much something's going to cost us. Next, we want to make sure, once we understand that, how do we allocate our funds in the best way possible? That's finding efficiencies, or also really making sure it's distributed in a way that really makes sense and delivers the most business value. And then the third is, I think one that is really important is, how do we become financially predictable? Especially when you're living in the cloud, there's it can be scary, right? You don't want to go to sleep and wake up with $100,000 worth of charges, because very well it could happen if you don't have the right controls in place. So how we started, right, from a budget standpoint, spreadsheet. I'm sure everybody loves those, and there's one pro, and it got the job done, right? So that is kind of day one, and it's okay to be there, right? The goal is to continue to evolve and kind of navigate away from that to something more robust. And the challenges as listed here: super manual intensive, required a lot of access control wasn't an issue, or not, was essentially non-existent to a degree. There's no centralized location of any of this data. Accuracy when it comes to budget requests and estimates were not great. And then there was also excessive handoffs when it came to getting a budget request from initiation to being accepted by ESDIS. How it evolved. The next big thing is we built something called the Crowd Resources Tool, also stands for CREST. And the way this web-based solution essentially works is, it is tenants or those that are living in the cloud go to the AWS pricing calculator. They say these are all the different services we plan on using, and they import that into the tool. The tool ingests that information, and it essentially translates into a way that our ESDIS counterparts care about. So we have different kind of cost categories. And then also it essentially builds out the 5 years of forecasting as well, which is required when it comes to cost modeling. The good things about that is automation heavy, right? We got rid of the spreadsheets, which everybody was happy about. We now had a centralized system of record. We had access control. And again, it got the job done, but a little bit better. Things we thought we really needed were now, okay, how do we continue to grow in this space and become more accurate in our estimates? And then how do we become more efficient, essentially eliminating the unnecessary excessive handoffs? Okay, how it's going and kind of where we are today. What you're seeing on the left-hand side has now changed because it's essentially showing you the integration of the cloud resources tool with machine learning. So what we're able to do now is we ingest historical data from all the different accounts that we have, over 200 accounts in AWS that live inside the Earth Data Cloud. We essentially ingest service level data about them, so we know exactly what service you're using, and then we have forecasts for those. So based on historical data, we forecast 18 months of it and essentially integrate that within the Crest tool and no longer require people to have to tell us how much they plan on spending. Essentially, we say, this is how much we think you're going to spend, and where there is user input required, we kind of have that room because we don't want to completely be automated in that way. So that human control still exists. And again, good things about that: automation heavy, centralized system of record. We eliminated the handoffs. We are way more accurate, and that's what you're seeing on the left-hand side, where the orange is kind of what we said we would spend, and then the dark greens are what we actually spent. And overall, that's when you look at it across the fiscal year, it's record numbers in terms of accuracy that we've seen. And then we also, because of this, we started to have different kinds of opportunities, which I will dive in here. Early stages, we were very much defensive, right? We wanted to just make sure we took that better safe than sorry approach. Wanted to make sure that costs were always managed, and it was very restrictive and to a degree a bit more on the reactive side. And kind of where we are today is what we call the measured response. We have super granular reporting and monitoring, and we'll talk about kind of how we've deployed that monitoring. And then we're calling what we have proactive. So essentially 911 calls you. So and it's instead of you having to reach out for help when something's happening, we essentially automatically know what's going on, and we say, hey, what's happening? Reach out to the tenants and essentially try to solve it. All right, so 2 quick ways that we've deployed this are all sort of around anomaly detection. What you're seeing on the left-hand side is the anomaly detection that happens around service level spending on a day-to-day basis. We essentially know how much you're expected to spend. If you're spending more than that by a specific threshold that we've established, we deem it an anomaly and we start to investigate. And that is done automatically. And it is right now. It's going to kind of our as this leadership. Next phase the tenants are actually going to start receiving these notifications as well. And then the next big one is we also do if you're anomalously spending against your budget. The first one is if we see any type of anomalous spending. But the second one is if you said you were going to spend $1,000 this month, it's day 2 and you've spent $500. That's clearly anomalous. There's something going on. So we reach out, an automated report that reaches out to the tenants and says, hey, you're spending at a rate that is essentially not sustainable. So those are the 2 big ways we've deployed our AI and ML to essentially be proactive and have that 911 calls you measure. And I'll pass it to Han for the last one there.
Yeah, I'm going to go back to Orbit to talk about the machine learning and AI capabilities of that. So before, for example, with the EMS analytics team, they had to go onto the hosted website, go page to page to download their data, have that download set to create more reports. Whereas with Orbit, they can access all of that on one space and then also comb through the existing data as well as new coming near real-time data to find insights across the board. And then there's also the machine learning function where if someone on the team might not be familiar with the coding aspect of it, they can write in natural language the queries that they want to create, the calculations they want to create, and it'll automate that for them, write out the syntax for them so that they can build more variables and filters and also collaborate at the same time with the same team members because it's a shareable space. And on the side, you can see the screenshot. Sometimes you just want a quick answer. So you can also use NLP and ask in natural language, like what are the top products in the last 3 months? And it'll give you the response as well as suggestions on visualizations and insights that you might not have thought about before. That's all we got.
We've got a solid 4 minutes for questions. So, have you got any questions about any of the talks we've seen today? No.
Was it double space? It was single space and 1-inch mark. Yeah.
All right, there's a protocol with this. You take the microphone and you ask the question, Nick. Does anybody have a question? If so, you can all just toddle off to lunch. Hey!
I think this is for Trevor. Trevor, you showed that the MCP connection didn't have a, yeah, you got to come up here. The MC connection didn't require authentication right now. How are you guys like tracking that? So I didn't know if it was like, I mean, is there any way to see metrics behind what's being queried or be like, you know, the DACs are doing this with their queries? Or I'm just interested to see what's coming out of it.
Yes, a little bit. Right now we're using LangFuse as an open source tool that allows you to trace conversations, so we can attribute different tool uses to different types of conversations. We can't look at the exact chats that users have had because those are on the AI clients, but we can look at a session and see all the requests that they performed within a session. We have work on the board to provide a tighter connection, a little bit more visibility, but right now we can get a pretty basic view of how users are using the tools.
Hey, come on up.
Okay, this is a question for the same group about the, I guess, the MCP service, but it may be a question for the community. So one of the things that, you know, I often think about when we present, you know, creating these MCPs is how are we conveying to the user whether they are using, say, quote unquote, best available science or best available data. And like that, evaluating what's the best available data, I think it's not something that the in-house team that's creating the data, that they're necessary, like they can give their opinions about that, but I think that's a question for the larger community. And so I've been thinking about like, how do we create these tools that can somehow, I don't know, be looking at the scientific data? What are people publishing about the data? What are the things that they are doing? It is evaluating the data and saying, hey, no, this one has errors, or, you know, hey, here are these two different data sources. This one, you know, tends to work better in these kind of situations. For example, like someone were looking at, hey, I'm interested in chlorophyll in coastal environments. Right? There's a lot of information in the literature people study, like what are the best algorithms for that? And how do we design these systems that not only are able to search our catalog, but are also somehow able to tap into the scientific community, get information from them, and at the same time, like create that cycle to like drive the scientific community to be evaluating these things. So they know like what the science that they're doing is also informing what the AI is coming up with. So again, it's a really broad question. It's not, yeah.
Yeah.
Just before you, that isn't an AI, new problem to AI though, right?
Yeah.
It was a problem before as well, so, yeah.
Yeah, I don't think you can like, there's a solid answer. I think it's more for the community. How do we?
Yeah, I think that right now we're relying a lot on the metadata to inform that. We have, you know, one of the tools I showed was the Get Citations tool. So an agent can explore, you know, here's an interesting data set. Let me go see what other papers cite this and see what collections are used in those data sets. And I think we're at a kind of weird time where the foundation models aren't quite super reliable, but if you anticipate that they continue on the progress that they're making, the more that this data is publicly available, it'll be encoded in the training, and these models will get smarter and have this knowledge for themselves rather than having to rely on external tools. And they can use these external tools to verify rather than making up the answer themselves confidently.
And I just wanted to add, I see in the chat on Zoom from Monica Morrison at NCAR that there's a new NSF grant out of CISL at NCAR that looks at leveraging semantic technologies like knowledge graphs to help with this, and that there's a session about how they're doing that on Friday.
All right, I think we're at time. I'd like to thank all my speakers dotted around the room, and Madeline, outstanding. Thanks, everybody.
I just wanted to let y'all know with the maze that is this meeting space, there's an elevator that's right out here. If you go down to the first floor and cross over the plaza, Tejas, which is where we'll have lunch, will be on your left. There should be people directing you, but I'll also be outside here too if you have any questions. And there are stairs. Yes, please. Yes, for sure.
Go get lunch. Thank you.